we are discussing the heat conduction problem in nuclear fuel core, and we have modeled the problem as Poisson's equation, that is del square U equals F type equation. Then in last lecture we have discretized this Poisson equation and we have developed a system of linear equation like AU equals B. We have decided to solve the system of linear equation using Gauss-Seidel type algorithm. So in this lecture, we'll review the Gauss-Seidel algorithm once again. Gauss-Seidel or any other iterative algorithm for n by n linear system solve this AU equals B problem, where A is an n by n matrix, U and B both are n-dimensional vector. Here A and B are known and we have to find U. The system can be written as a summation of j equals 1 to n aij uj equals bi for I equals 1 to n. For each of this I, we will get one linear equation. For I equal to 1, for instance, I'll get A11 U1 A1 to U2 up to A1 and UN equals B1. I equals 2, I'll get A21 U1 plus A2 to U2, etc. I equals n, I'll get A1 AN1 U1 plus AN to U2 up to ANN UN equals Bn. Now, we have learned Jacobi iteration to solve this. Jacobi iteration, what it does is that when it is solving, let us say for U1, it takes this equation 1 and it keeps this A11 U1 on the left hand side, everything else it puts on the right hand side, then divide both sides by A11. So in a sense then U1 will be given by B1 minus everything else other than U1 will from left hand side will go there, and then I divide by A11. So I get this estimate of U1 at kth iteration, but all other U's on the right hand side is at k minus 1th iteration. Again, when I am solving for U2, I come to this equation, but I follow the same procedure here. U2 is on left hand side, everything else I have taken on right hand side, and moreover, all other U's I have taken at k minus 1th on the right hand side, only the left side U2 is at kth iteration. When I am calculating this, I already know the value of U1 at kth iteration, and yet I am still using the k minus 1th iteration value of U1 here. So we can generalize this idea by writing Ui k is Bi minus everything else other than Ui. That is why j is summed over 1 to n, but j not equal to I. J equal to I will be this Aii Ui. To write it in a better way, what we do is that we take this not equal to out, which means we sum all of them. But when we sum all of them, we have one extra, this Aii Ui. So I take this Uii Ui out. So this is actually much easier to implement, as you will see quickly. This Aii Ui divided by Aii gives us Ui k minus 1. So overall algorithm now become Ui k equals Ui k minus 1 plus Ri by Aii, where Ri is this entire term, Bi minus everything of left hand side that is there in the equation I. Now in an ideal world, this Ri should be 0. Then we can say that we have reached the solution, but certainly it is not 0, and that is what is bringing some correction here. As the solution approaches the correct solution, this correction will be less and less, and Ri will go toward 0. This particular idea is true for iterative schemes, but actual correction here, that will vary from scheme to scheme. Now, let us see that how we'll make this in Gauss-Seidel. The basic difference between Jacobi and Gauss-Seidel is that when I'm calculating the correction here in Jacobi, all the u's are at k-1th iteration, but at this point I know some of the u at kth iteration. So in Gauss-Seidel, I use the latest values of u, whatever I know from the kth iteration or k-1th iteration. That is the only difference between Jacobi and Gauss-Seidel. So for instance, if I solve these two equations, 10u1 plus u2 equals 11 and u1 plus 10u2 equals 11, then the Gauss-Seidel algorithm will go like this: u1 in kth iteration equal to 11 minus u2 in k-1th iteration divided by 10. From this, I get this u1 at kth iteration. Therefore, when I am trying to find out u2 at kth iteration from this equation 2, I use u2 at kth iteration equals 11 minus u1 at kth iteration, not k-1, divided by 10. So it is always using the latest value, whatever it is known. In Jacobi iteration, here we would have been using k-1 iteration in u1, even though u1 k is known. So keeping this in mind, our Gauss-Seidel algorithm is very similar to Jacobi. uik equals uik-1 plus correction, and correction is ri by aii. But what happens that ri, I go from j equals 1 to I minus 1. That is already I have, because I am evaluating ui here. So 1 to I minus 1 I have already calculated in kth iteration. So I am taking their kth iteration value. But then starting from I to n, remaining part, I have taken their k-1th iteration value because I still don't know their kth iteration value. To stop this iteration, I'll say that when my au minus b, this is a vector, the norm of that vector, when it would be small enough, will stop the iteration. But this norm of the vector can be easily calculated, that is connected to ri. So it can be easily calculated from ri. Now we come to successive over-relaxation, and in this case we introduce a weight factor. This is a positive real number, what we call relaxation factor here. If this weight is 1, then it doesn't make any change in Gauss-Seidel, it is just the classical method. If it is greater than 1, we call it is over relaxation. If it is less than 1, this is under. When it is greater than 1, we are adding more correction. When it is less than 1, we are reducing the correction suggested by Gauss-Seidel. So now to summarize, we have to remind you that even though we have discussed Gauss-Seidel with successive over-relaxation, this over-relaxation factor requires trial and error. We cannot casually pick one factor. Solver will slow down or diverge if we take higher than optimum relaxation factor. This relaxation factor depends on matrix A only. So when we are solving AU equals B1, AU equals B2, etc., many times, then we can trial with one of this system and we can get a relaxation factor. And then we can use that relaxation factor subsequently. But in this case, we will solve AU equals B1. So relaxation factor, unless you are really convinced, will probably not be very useful here. For your exercise, taking A as a pentadiagonal matrix, which is true for the case that we will be solving, you write a pseudocode for GSSOR for solving AU equals B. This pseudocode writing is important because we will convert this pseudocode to a computer program later on. Thank you. That's all for now, and I'll see you in next class.